Welcome back. In this video, we're going to talk about how regular expressions are used to construct a full lexical specification of a programming language. Before we get started, I want to quickly summarize notation for regular expressions. One of the shorthands we talked about last time is A+, which means a sequence of at least one A, or the language A star. Sometimes you'll see a vertical bar used instead of union, so A plus B can also be written A vertical bar B. An optional A is an abbreviation for the regular expression A plus epsilon. And then we had character ranges, which allows us to do a big union of a bunch of characters in order. And then one more that's used that's actually fairly important, but we didn't discuss last time, is the complement of a character range. So this expression here means any character except the characters A through Z. So in the last lecture, we talked about a specification for the following predicate. Given a string S, is it in the language, that's the function L, of a regular expression? That is, we defined a language of regular expressions, and we talked about their semantics in terms of sets of strings. And so for any given regular expression, we could reason out by hand whether a given string was in that language or not. And this turns out not to be enough for what we want to do. So just to review, what is it we want to do? Well, we're given an input, which is a bunch of characters. So here's a string of characters. And it can be much longer than just 7 characters. And what we actually want to do is to partition this string. We want to drop lines in this string to divide it up into the words of the language. Now, of course, each one of these words ought to be in the language of some regular expression. But just having a definition of a yes-no answer is not quite the same thing as having a method for partitioning a string into its constituent parts. And so we're going to have to adapt regular expressions to this problem. And that will require some small extensions, and that's what this video is all about. So let's talk about how to do this. The first thing we're going to do when we want to design the lexical specification of a language is we have to write a regular expression for the lexemes of each of the token classes. And we talked about how to do this last time. So for the numbers, we might use digit plus as our regular expression, and we might have a category of keywords, which is just a list of all the keywords in the language. We will have some category perhaps of identifiers. There's the definition we talked about last time, sequences of letters or digits that begin with a letter. And then we'll have a bunch of punctuation, things like open parens, close parens, etc. So we write down a whole set of regular expressions, one for each syntactic category in the language. And that's the starting point for our lexical specification. Now, as the second step, what we're going to do is we're going to construct a gigantic regular expression which just matches all the lexemes for all the tokens. And this is just the union of all the regular expressions that we wrote down on the previous slide. So we just take the union of all those regular expressions, and that forms the lexical specification of the language. And we'll just write this out. We don't really care what these regular expressions are, but they're just some set R1, R2, and so on, and the whole thing we're going to call R. And now here's the heart of how we actually use this lexical specification to perform lexical analysis. So let's consider an input. The input's a string x1 up to xn. And now for every prefix of that input, okay, we're going to check whether it's in the language of the regular expression. So we're going to look at some prefix starting with the first character, and we're going to ask ourselves, is it in the language of that big regular expression? And if it is in the language, well, then we know, in particular, that that prefix is in the language of one of the constituent regular expressions, because remember that R is equal to the sum of all the different token classes of our language. Okay, so we know that this prefix x1 through xi is in the language of some rj. Okay, and so that we know that that's a word in our language. It's it's in one of the token classes that we're interested in. And so what we do is we simply delete that prefix from the input, and then we go back to 3, and we repeat. And in this way, we keep biting off prefixes of the input, and we'll do this until the string is empty, and then we have lexically analyzed the entire program. Now, this algorithm has a couple of ambiguities. There are a couple of things that are underspecified, and those are actually interesting. And so let's take a moment and talk about those. The first question is how much input is actually used. So let's consider the following situation. Let's say that we have that x1 through xi is in the language of our lexical specification. And let's say there's a different prefix that's also in the language of our lexical specification. And of course here I is not equal to j. Now what does that look like? Well, it would look like the following kind of situation. We would have our input string, and we have two different prefixes of the input that are both valid token classes. And the question is, which one of these do we want? And just to be concrete here, to give a concrete example, let's consider what happens when a double equals is at the beginning of the input. So after we've chopped off a bunch of other input, perhaps we have this substring or this prefix of the input that we're looking at, and the question is, should this be regarded as a single equals, which would be an assignment operator in most languages, or would it be regarded as a double equals, which in some languages is a comparison operator? And this is an example we've looked at before and discussed, and there's actually a well-defined answer to this question, and it is that we should always take the longer one, and this has a name. It's called the maximal munch. So the rule is that when faced with a choice of two different prefixes of the input, but either of which would be a valid token, we should always choose the longer one. And the reason for this is that's just the way humans themselves read things. So when we see a double equals, we don't see two different equal operators, we see a double equals. And if I look at at this sentence that I wrote up here, when we look at HOW, we don't see three letters. We gather that all together in one long token. We go as far as we can until we see a separator. And so because this is the way humans work, we make the tools work the same way. And this normally, or almost always, does the right thing. A second question is, which token should be used if more than one token matches? So what do I mean by that? Well, again, we have our prefix of the input, and it's in the language of our lexical specification. And just remember that the lexical specification itself, again, is made up as the union of a bunch of regular expressions for token classes. Now, since this prefix is in the language of the lexical specification, that means that it must be in the language of some particular token class, RJ. But nothing says that it isn't also in the language of a completely different token class, meaning that this same string could be interpreted as one of two different tokens. And the question is, if this happens, which one should we pick? So, for example, just to make this concrete, recall that we could have a lexical specification for keywords, which would be things like if, and else, and so on, and also for identifiers. And an identifier was a letter followed by a letter or a digit repeated. Okay. And if you look at these two specifications, you'll see that the string if is both of them. So if is in the language of keywords, and it's also in the language of the identifiers. And so should we treat if as a keyword or an identifier? Now, the normal rule in most languages is that if it's a keyword, then it's always a keyword, and the identifiers actually don't include the keywords. But actually, it's a real pain to write out the identifiers in such a way that you explicitly exclude the keywords. This is a much more natural definition that I've written here for the identifiers. And so the way this gets resolved is by a priority ordering. And typically, the rule is to choose the one listed first. Okay? So when there is a choice, when there is more than one token class to which a string might belong, the one that is listed first is given higher priority. So in our file defining our lexical specification, we would put the keywords before the identifiers, just as we have done here. The final question is what to do if no rule matches. What if I have a prefix of the input that is not in the language of my lexical specification? Now, this can actually arise. Certainly, there are lots and lots of strings that are not going to be in the language of the lexical specification of most languages. And the question is how to handle that situation. So it's very important for compilers to do good error handling. They can't simply crash. You need to be able to give the user, the programmer, feedback about where the error is and what kind of error it is. So we do need to handle this gracefully. And the best solution for lexical analysis is to not do this. So don't let this ever happen. Okay, so what we want to do instead is to write a category of error strings. So all the strings not in the lexical specification of the language. So we write out a regular expression. Again, this is another regular expression here for all the possible error strings, all the possible erroneous strings that could occur as invalid lexical input. And then we put it last. Put it last in priority so that it will match after everything else matches. And the reason for putting it last is that this actually allows us to be a little bit sloppy in how we define the error strings. It can actually overlap with earlier regular expressions. We can include things in the error strings that are in fact not errors. But if we put it last in priority, then it will only match if no earlier regular expression matched. And so in fact it will only catch the error strings. And then the action that we'll take when we match the error string will be to print an error message and give the nice feedback like where it is in the file and such. To wrap up this video, regular expressions are a very nice and concise notation for string patterns, but to use them in lexical analysis requires a couple of small extensions. So in particular, there's a couple of ambiguities we have to resolve. We want our matches to be as long as possible. So we take as much input at a time as we can, and we also want to choose the highest priority match. So the regular expressions are given a priority, the different token classes have priorities, and when there's a tie, when the same prefix of the input could match more than one, we pick the one that has the highest priority. And typically this is done just by listing them in order in a file, and the ones listed first have higher priority over the ones listed later. I just want to warn you that when you go to write lexical specifications, when you go to actually implement Lexar for a language, the interaction of these two rules, that we take the longest possible matches and we break ties in favor of the highest priority rules, that these lead to some tricky situations, and it's not always obvious that you're getting exactly what you want. You have to think carefully about the ordering of the rules and exactly how you write the rules so that you get the behavior that you desire. And finally, to handle errors, we typically write out a catch-all regular expression that soaks up all the possible erroneous strings and give it the lowest priority so that it only triggers if no valid token class matches some piece of the input. And finally, we haven't discussed these yet, but there are very good algorithms known for implementing all of this. And in fact, we'll be able to do it in only a single pass over the input and with very few operations per character, with just a simple table lookup. And this will be the subject of our future videos.